listen from on this topic.
Okay. Thank you very much for the introduction and also for the invitation. As Vera said, we have lambda called dark matter. It's it's a very satisfactory model because it can predict and reproduces most of the observations with very good precision, but it still has some problems at the theoretical level because, for example, it relies in cold dark matter but doesn't attempt to have a microscopic description of its nature, and also it just assumes a cosmological constant for dark energy, and again does not provide an explanation for it. It also has some problems at the experimental or observational level that are these tensions that Ophelia mentioned, that are basically the main topic of this course. Is going to be basically focused on the Hubble constant tension and the tension on the clustering at small scales. And as we will see, there are like some general trends that basically this tension appear between observations at high redshift, mostly the CMB, and observations that depend on the local or late universe. But in order to be able to talk about these topics, we will also need to introduce a bit some of the main observables that we are going to cover. So during the first lecture, I'm going to be basically giving a super quick recap of cosmology and the growth of perturbations. The objective of today's class is going to end with how matter perturbations grow and the matter power spectrum at the late times. Tomorrow, we're going to study the CMB in a simplified way in order to basically have an understanding of the main features on the CMB power spectrum, in order to, on the third class, see how we can measure H-naught or infer H-naught from the CMB, and also discuss some of the main other ways to measure H-naught at lower redshift to understand how, like, the potential reasons or like the potential ways where new physics can enter to solve the tension. But we are going to leave the discussion about those models till the last day, because on the fourth day, I'm going to be talking mostly about lensing and the ways to measure in the clustering at low redshift and at the smaller scales where this tension appears. If you have any question or anything, just feel free to interrupt me, or you can just grab me in any of the breaks or in the afternoon and just ask me anything or discuss anything that you want. For those of you that are doing cosmology, some of these classes are going to be maybe a repeat of some things that you know and already studied. But I'm sorry, since like I assume that the background of all of you is quite diverse. So I think that this way is better in order for all of us to be on the same page. So as I said, today I'm going to give a recap of cosmology, perturbation theory, and growth of perturbations. And during the whole course, I'm going to be using, unless otherwise stated, natural units. And I'm going to be working on Fourier space, because that way we can change an infinite number of coupled differential equations to just a closed system of differential equations in which, at linear level, each Fourier mode is totally independent from the rest and is much easier to evolve. Okay, so we've been talking about cosmology and the universe and so on, but basically it's based on two very simplifying terms. That is basically that we want to study the nature and the evolution of the universe and its component, but we want to do it in a statistical way. And basically that is a very big difference with respect to astrophysics, because rather than focusing on single objects or specific astrophysical bodies, we are going to be using only general relativity and a lot of statistical mechanics. And basically that relies on two main set of equations. On one hand, we're going to have the Einstein equations that are the ones that relate matter and radiation with gravity, in general relativity, of course. And on the other case, we have, for statistical mechanics, the Boltzmann equations. So on one hand, we have as I said, Einstein equations, which is basically relating the Einstein tensor, that is a tensor that depends on the metric and derivatives of the metric, which is g mu nu. This is the famous cosmological constant tensor that doesn't affect otherwise the equations, but can appear as an accelerated term for the scale factor. And this is the term that relies on the components of the universe with the stress energy tensor, which is basically the description of the energy and momentum of the components of the universe. And on the other hand, we have the Boltzmann equation, which is basically the time evolution of the phase space distribution of any specific component of the universe. The phase space distribution could be f here, and if we expand the time derivative, we will then with the expanded Boltzmann equation. Where dots are time derivatives. And this is the gradient with respect to the position and the gradient with respect to the potential in the phase space. And this one is the collision term that basically describes all the interactions between particles and so on that are not described through gravity. This, for example, could be on the case of the photons and the baryons, where the collision of the Compton scattering could appear. If we don't have any of these interactions, for example, for cold dark matter, this would be zero. And all the effects on gravity are actually on how the position and the momentum of the particles evolve. And this is basically related with gravity because under the assumptions of general relativity, particles move in geodesics, and these are going to depend always on the metric and its evolution. Okay, another one of the base assumptions that we're going to do for this course and for cosmology in general is that we can see that for most of the evolution of the universe is very, very smooth, and there's only small fluctuations around it. So that's why we can apply perturbation theory, and we're going to be discussing all the time between the background expansion and the growth of the linear perturbations of it. We can expand this to higher order terms in perturbation theory, but for most of the evolution of the universe, linear perturbations are enough, except for matter perturbations at small scales and very low redshift. And the metric in the background expansion that we're going to use is the Friedmann-Lemaitre-Robertson worker. Sorry, IJ, which is a diagonal metric. It only depends on the scale factor that describes the evolution of the universe, the expansion of the universe as function of time. And I'm going to be using all the time the mostly positive signature. And this is in terms of the physical time, but most of the time I'm going to be using conformal time in such a way that we can express this as this. Sorry, this is conformal time, where, no, this is the other way around. Yes. The relation between the conformal and the physical time is just a factor of the scale factor. And now from this metric, we can actually express the first division between background and perturbations. We can write g mu nu as the background term plus some small perturbations, and this is where all the evolution of gravity is going to appear, where there we will have, for example, the evolution of the potential and so on and so forth. For this, in principle, we will have many terms that we can tweak in the perturbation of the metric. In principle, we will have 10 degrees of freedom. We can apply the scalar vector tensor decomposition here and see that we will have 4 scalar degrees of freedoms. We will have 4 degrees of freedom also in vector components because we will have 2 transverse vectors, and finally 2 tensorial degrees of freedom. But we are going to be considering all the time only scalar perturbations for, I think for most of the course, if not all. And therefore, we are going to ignore tensor perturbations that are those related with gravitational perturbations and would be generated by inflation and propagate in the forms of gravitational waves from the primordial universe. Vector components, if generated in inflation, they would decay quickly, so we wouldn't have any of those, and that's also basically one of the assumptions of the cosmological principle, because a vector perturbation will have some preferred direction. And finally, from the 4 degrees of freedom that we have for the scalar perturbations, we need to actually reduce it to 2, which are the physical ones, because the other are a matter of a choice of coordinates, which is basically the discussion of the gauge and the choice of gauge. Now, this is something that the physics at the end of the day, of course, need to be the same, but sometimes the calculations are going to be easier or more complicated, and we're going to be working all the time in the Newtonian gauge, which is still a diagonal metric, and depends on the 2 gravitational potentials. So now we will have to determine A squared from the background expansion of the universe, and we will have to study how psi and phi, which are the gravitational potentials, evolve with time and with a scale. We can also apply the same kind of perturbation theory for the phase space distribution. And in this case, we will have that the phase space distribution, which must depend only on the, the phase space distribution, which in general depends on the position, the momentum, and I'm going to be using Q as the conformal momentum and separating between the direction of the momentum and the magnitude and time. We can separate it in some background term, and of course this one, since the background is homogeneous and isotropic, can only depend on the norm of the momentum and the mass of the particle that we are talking about, and we can have some perturbation here that depends, this one, on the position, momentum, direction of the momentum, time, and the mass. So for example, if we are talking about relativistic particles, this would be the Fermi-Dirac or the Bose-Einstein distribution, depending on whether they are fermions or bosons, and this would be perturbations around that. And if we basically substitute this here and take into account the metric for these terms, we will end to some evolution for the for both the background and the perturbation that goes like this. for the background and for the perturbations. Okay. Where I have defined epsilon is equal to the scale factor times the energy, Q, as I said before, as the co-moving momentum, which is the scale factor times the physical momentum, and mu is the cosine between the angle of the direction of propagation of the particle, the direction of the momentum, and the wave mode that we are considering. Now, of course, from here to here, there's a lot of steps of derivation. In the notes that I'm going to provide, we still need to decide whether day by day or at the end of the course. You can find all the derivation if you want to check that. But from here, there are already a couple of impact that we can discuss. This one basically tells us that the relationship between the energy and time for the phase space. But interestingly, at the level of the perturbations, the only dependence that we have in the direction of the momentum at linear level is through the angle that it has with the wave mode. That at the end of the day is related with the spatial gradients that we will take with respect to the direction of the momentum. But dealing with this angular dependence is very complicated, and that's why in cosmology we take all the time expansion in Legendre polynomials of this phase distribution, because it's easier in the same way that it was easier to deal in Fourier space with the position. Here for the angle, we prefer to expand the perturbations of the phase space in terms of the coefficients of a Legendre polynomial expansion. And also for massless particles, note that the energy is equal to the momentum, so we will be basically canceling this term and this term, because those factors would be 1, and we can integrate out any dependence of the momentum. So for example, the photons, which is one of the main properties that we are going to cover, and components of the universe, we can define F gamma here that would depend on K, mu, and tau as the momentum integrated phase space over only the background. And this is one of the quantities that we can expand in Legendre polynomial. In which here, this one is going to depend only on the wave mode that we are interested in, and the time, and of course, the multiplication over the Legendre polynomial. So basically here we have transformed something that, depending on position, momentum, direction of the momentum, and time, into something that depends on the wave mode, but each of those are going to evolve independently between them. And all the dependence on the momentum for particles that are massless, we can take it out and leave our equation only in terms of the time and k for each coefficient of the Legendre multiple. This involves some problems also because, as you can imagine, this is an infinite series, and if we go from if we apply the definition of f gamma here, the equation looks like still in terms of mu plus ik mu f gamma plus 4 times phi prime ak mu side is equal to the collision term. So now we have this differential equation for the properties of the phase space distribution. And the point is that we are going to transform this in an infinite system of differential equations, removing the dependence of mu, and that's what is called the Boltzmann hierarchy, because each multiple L, here for the coefficients of the Legendre expansion, is going to depend on the previous monopole, on the previous multiple, and the multiple above it. And this is a problem in cosmological perturbation theory because, for example, for particles that free stream, we need to take into account a lot of multiples for this expansion, and we would end with a lot of differential equations, and we need to find a way to close the Boltzmann hierarchy. There is where different sets of approximations can help to close this system and this hierarchy. But at the end of the day, you need to decide that. And currently, cosmological Boltzmann-Einstein codes, as for example, class or CAM, that I'm sure that some of you use quite a lot. We need, for example, I think it's like of the order of 17 differential equations only to describe the evolution of the photons in terms of these multiples. Most of the times, though, for the analytic understanding that we are going to have during these classes, we are going to neglect most of those and keep things simple. But why I'm saying like all these things about the Boltzmann equation and why these things are important, and it's basically because we can relate the properties of the component of the universe, the species that we are describing with this Boltzmann equation, to the total energy stress tensor that is the one that determines the Einstein equation. So basically, at the end of the day, we have that the energy stress tensor, it's this prefactor that accounts for the number of the analyses that we have. For example, if we are talking about a spin 1/2, since a spin doesn't have a big impact in cosmological perturbation theory, this would be a factor 2. And this is a geometric factor, which is minus the determinant of the metric, and basically is to obtain that the covariant derivative of the energy momentum tensor is 0. And then here we have the weighted integral of the phase space distribution, where these are the form momentum, the spatial components of the form momentum, and then we have the weights here for the integral of the phase space. And here there are a couple of interesting things. This 2 pi cube comes from the Heisenberg principle because we can't localize any particle with a precision better, like in phase space, within a volume smaller than 2 pi h bar cube. And since we are working on natural units, that's why the h bar term isn't there. And then from here we can also see some of the properties and understand how all these enter the energy momentum tensor. So for instance, the number density of a particle could be just the integral of the phase space distribution without any weighting, because basically you would marginalize over the properties of the momentum and will leave only the number density of that particle in that position. The form momentum density it's the integral weighted by the momentum. And then this part is the form momentum current density by adding also the P mu and P zero. That is actually what the energy momentum tensor leaves. So what are the components of this energy momentum tensor? Okay, so the 0,0 component is going to be minus the number density. The space 10 components are number density and pressure times the bulk velocity of the fluid. The other one is the same. And finally, the space component has a term that goes as the pressure only in the diagonal plus the anisotropic stress. That could be the pressure that could go in different directions for the, this is like a traceless term. And from here, we can also do the same kind of distinction between the mean background plus small perturbations in such a way that the mean background would be only the mean density and the mean pressure here, because the bulk velocity and the anisotropic stress are already linear in perturbation theory. So for the background, we can remove it. And we have here the perturbation components. 0, and this is Bi. For the ij is the same. And here we have only the perturbation of the pressure plus the anisotropic stress. And now we are going to be caring always about the total energy momentum tensor, but we know the evolution for each independent component of the universe and each independent species. So it's a matter of solving the Boltzmann equation for each independent case. Go here, compute the energy momentum tensor for each independent species, and finally add all of them to be fed in the Einstein equation. So at the end of the day, the system that we have combining general relativity and statistical mechanics, it's general relativity, like the gravity, is determined by the total components and the total energy and momentum in the universe in terms of form of matter. That itself, it's informed in the evolution by the evolution of the gravitational potentials. And this basically a crossover system. I'm going to be using also quite a lot some definitions here that are just reweights of this. So for each individual species, I'm going to consider that delta S is the perturbation in the density in the energy density for that species over the mean. I'm going to be working rather than with the bulk velocity of the fluid or the species in general, with the velocity divergence. So in this case, this is for each one. And then I'm also working with the shear that is obtained also as the divergenceless and trace-free part of the anisotropic stress. Over sigma, of sigma ij. But taking into account that, for example, delta tot is not going to be only the sum of delta S, because what is going to be delta tot is the delta of the perturbation in the total density over the total mean density, so we need to take that into account when computing the total quantities. So for example, if we think in terms of these variables for the case of the momentum average multiples of the phase space distribution, that's okay. We have that, for example, for photons, the perturbation, the normalized perturbation in the energy density is equal to the monopole in the momentum average phase distribution. What is corresponding to theta S, so theta gamma would be proportional to the dipole. And the shear is proportional to the quadrupole. Which makes sense, right? At the end of the day, the monopole will give us the overall isotropic distribution for the energy. The dipole is how that is distributed in a specific direction, and that's why it's related with the velocity divergence. And for the shear, we start having contribution that goes in two directions, and that's why it's related with the anisotropic stress. So for photons, for example, or for neutrinos and particles that depend on the whole Boltzmann hierarchy because they free stream, we are going to be working with the multiples of the phase space distribution, but for other fluids, such as, for example, cold dark matter or baryons that can be taken as fluids, they don't have if they are like, since we are taking them as perfect fluids, they don't have the stress, the shear, and we are going to be left all the time with just the first two moments, the energy density and the divergence of the velocity. Okay. So basically now we know G in terms of the metric. T is informed by the Boltzmann equations, so we can already go and try to solve the, we can derive the evolution equations for the Einstein equations both at the background and the linear perturbation theory. Again, this derivation, the algebra is very easy, it's straightforward, but it's cumbersome. It's just like take some pages of computation, so I'm not going to go through it, but you can take a look at the in the notes. And from there, we end up with some of the equations that I'm sure you are very familiar with. And this is that at linear level, at the background level, we can define H square, which is the Hubble parameter, as 8pj the mean density, and we can also express this in terms of the Hubble constant, which is going to be one of the main topics of the course. This is basically the current expansion rate of the universe times the sum of the density parameters that I'm going to define now times the scale factor to the -3, 1 plus the equation of state parameter for each species. Now here, H is A dot over A, the expansion rate of the universe. I'm going to be using quite sometimes some curly H, which is the same but in conformal time. Omega S is defined as the mean density for that specific over the critical density, which is the one defined as the one that closes the universe just perfectly. The equation of a state parameter that is going to appear also quite sometimes is just the ratio between the mean pressure and the mean energy density for each species. So for example, here for collisionless non-relativistic components, such as for example cold dark matter, there's no pressure, the equation of a state parameter is 0. For free streaming particles, such as for example neutrinos or photons, this is going to be 1/3, so on, and that's what goes here to express all the evolution of the Hubble parameter in terms of each specific quantity. And I'm going to be assuming most of the time that we consider a flat universe, but if not, here there would be also the relation from the curvature. Now here, for example, if we are in radiation-dominated epoch at the very early times with all the energy density of the universe is dominated by relativistic particles and radiation, the expansion rate is going to evolve as a to the -4. But on the contrary, if we then go to the matter-dominated epoch, this is going to evolve as a to the -3. And that changes on how the expansion rate evolves with time and so on and so forth. We're going to see just now that has a lot of implications on how the perturbations evolve. There's also a second equation that describes the acceleration of this, like the acceleration of the expansion universe, like the second derivative of the scale factor, but it's not going to be super relevant for what we're going to be discussing. So if you let me go to linear order, the equation that we're going to have is basically from taking different components from the space, from the Einstein equation, and from the trace of the space-space component, we would get that basically the Laplacian of the sum of the two gravitational potentials depends on the sum of the mean density and the mean pressure times the shear. And this is also a very important result, because if we don't have particles contributing to the energy density that free stream, the shear is going to be 0, and that means that in a sorry, in a universe in which we can neglect the shear, so if sigma is equal to 0, the two gravitational potentials are the same with the opposite sign. Now, this condition is never going to be actually true, but in many cases we are going to be able to make that approximation, and we are going to basically be doing it all the time. And that's because before recombination, baryons and photons are tightly coupled in such a way that they can be treated as a perfect fluid, because the quadrupole is going to be very suppressed. And also, the other component, the other species in the universe that creates the shear would be the neutrinos, but their contribution to the energy momentum tensor and to the growth of perturbations is very small, and we only need to care about it when we are going to do actually precision cosmology. So for your calculations and the codes and everything, that must be taken into account, but if we want to get an analytic understanding of what's going on, which is what we're going to be doing most of the time, we can do this assumption. From the time-time component of the Einstein equation, we have that the Laplacian of phi times 3 conformal Hubble, the time derivative of phi minus Hubble, conformal Hubble times psi, is equal to 4 pi GA squared and the mean density times the perturbation. And here you can see that this is the generalization in general relativity of the Poisson equation. Because if we would be totally in a matter-dominated universe and well within the horizon, where basically the expansion history of the universe and the time derivatives of the potential doesn't matter that much, we would be in a case in which we have k squared of phi is equal to 4 pi j a squared delta m and rho m, which is the standard Poisson equation. This is only if we are in a moment that are much later than matter radiation equality and well within the horizon. So the horizon, I'm going to define it a bit later, but it's basically where the relativistic terms on how the expansion of the universe are less important, and we can assume a Newtonian gravity. So as you can see here, well, we can also write another one relating from the space-time component that relates the potentials to the divergency of the velocities. And from here we have how the universe expands, the background universe expands. That is going to depend whether we are in radiation-dominated epoch or in matter radiation epoch, or if we are today, we would be starting a regime in which dark energy is dominated, and that's why H is not going to depend on A at some point, and the universe expansion is accelerating. And then, at the linear level, we have, as I was saying before, the equations that depend on the perturbations of the metric, that are the gravitational potentials, in terms of the main properties of the energy momentum tensor, that would be the density, the velocity or momentum, and the shear, that we track solving the Boltzmann equations. And this is basically what you feed to the and what is coded in this Einstein-Boltzmann code that I mentioned before, and the system of differential equations that is solved at the end of the day in order to evolve the growth of perturbations. Now, since this is a system of differential equations, the only thing that is left to basically be able to solve it and give an actual solution is some initial condition. That is what where inflation plays a role. Okay. Yeah. Okay, we can take a break now, like 5-10 minutes or something like that. And after, we are going to basically discuss very quickly the initial conditions and how they are. And basically, we're going to use all this to get the evolution of the matter perturbations in the universe. Okay, see you in a bit. So yeah, we can go on now, but from some of the questions that some of you asked me right now, I acknowledge that I've basically have gone through what can be a whole course of cosmology in half an hour. So sorry for that, but I just needed to go through some of the basics and some of the definitions because I'm going to be using them now. I hope that during the during the week, you get more familiar with some of these things when we explain things in a more factual way rather than completely formal on the blackboard and everything. We can discuss more things with the hands and understand the physical intuition about it. But in any case, feel free to come to me. I'm going to upload the notes as soon as I can, and then on the notes, you can basically see the whole derivation and the whole discussion of all that. But as we were saying, we basically have two equations that describe the evolution of the gravitational potentials or the perturbations of the metrics. I'm talking about gravitational potentials because in the Newtonian gauge, we can understand phi and psi as something very related with the standard Newtonian potential. But if we were working in any other gauge, those would have a different meaning. And we have those coupled to all the set of Boltzmann equations that describe the evolution of the properties of each independent species in the universe. In all generality, in lambda CDM, we can consider cold dark matter baryons that have the same properties as cold dark matter, but they interact with photons through Compton scattering. And at very small scales, we'll have also the self-interaction because of the astrophysics and the dust and so on. And then we have also photons and neutrinos that in most cases, since cosmology is sensitive to the total mass of the neutrinos, but it's very non-sensitive to the individual masses of them. Usually what we do is consider a massive neutrino and two massless neutrinos because the equations then simplify much more in that case. But as I was saying, we still have left the initial conditions in order to set the initial point and be able to give an actual solution for this system. Now, with inflation, I'm going to do something even worse than for cosmology, so I'm going to cover it in like 5-10 minutes. Sorry for that, but it's basically a theory that was developed to give some initial conditions of the universe and to complement what was the Big Bang theory before, that basically the universe at the beginning was very compressed, very energetic, and very homogeneous fluid, and then it expanded, it cooled until we see what we have. But the Big Bang theory had some drawbacks, and it's basically related with the horizon problem, which is basically why from the CMB we observe that it's very homogeneous and very smooth, and when actually two different patches of the sky at the time of the CMB were causally disconnected. So there's no reason to assume that it was going to be like that. And then the flatness problem, that is basically assuming just a standard Big Bang setting, the fact that today we observe the universe as flat involves a extreme fine-tuning at very early times. So basically, the way that inflation can solve this is assuming some primordial phase of accelerated expansion, in which this expansion is actually exponential. So for that, the Hubble rate is actually almost constant, such as we can have A as e to the ht. And the simplest flavor of inflation involves an scalar field, which is the simplest particle that we can imagine in order to describe this negative pressure that would contribute to the accelerated expansion of the universe. And as I was saying, in order to be able to get this constant age and the exponential expansion, this field needs to evolve very, very slowly. And that's why it's a slow roll inflation that probably most of you have heard about at some point. And also, and very importantly, this is a single field, in the simplest case. So in this single field slow roll inflation, basically what we have is a single species driving the evolution of the universe in such a way that each position in space that is going to be determined by the mean value of the field, but also by a perturbation of that field in that position, can be described as being slightly ahead or behind in time. And that's why some people talk about the single field slow roll inflation as having a single clock for the evolution of the universe. And that's why this kind of inflation predict only the generation of adiabatic perturbations. That adiabatic perturbations are described and defined as being just that all perturbations at that moment in a single space at a given conformal time can be described as some small time shift. And the time shift as a function of position because it's related with the perturbations in the scalar field. Now, if we expand this, we have that this depends on the conformal time of the mean density times that time shift in such a way that from this we know the relationship for all species because it depends on how they evolve with time, right? So a given species is going to go as some other and the fraction of this is the equation of state parameters from each of them. And this is why, for example, for adiabatic perturbation, the perturbations in the matter are 4/3 of 4/3, 3/4 of the perturbation in the photons. Basically, because the equation of state parameter for cold dark matter is 0, and for the photons is 1/3. So you have this relationship for all of them. Now, we were talking before about the choice of gauge and why is this important in order to solve some of our calculations, but that also involves that there are some quantities that are very important in cosmology that are the gauge invariant quantities. That is some quantities that are going to have the same expression in any gauge. And one of them is the curvature perturbations that are basically the way and the species for the perturbation that has been chosen in order to describe the primordial perturbations in the metric. And this is because these perturbations are related with the expansion rate of the universe, just as the particles, as the modes, sorry, leave the horizon, and are frozen outside of the horizon. So let me first of all introduce the horizon, and then describe how the horizon evolves for a given mode as function of time, and how we can, or like the expression for the primordial power spectrum of curvature perturbations. So. We have here adiabatic perturbations. And then the horizon is basically the comoving distance that the light can travel in a given time. And this is because that's going to be the maximum distance in which two patches of the sky or two positions are going to be causally connected, because the interactions are not instantaneous. So in that case, the size of the horizon is just the time integral over the scale, or in conformal time, just the integral of the conformal time, that is tau. And this is why when working in natural units, sometimes the conformal time is also given in units of distance, in units of megaparsecs. As you can imagine, here there's like a speed of light factor that is equal to 1 in natural units. So from here, since the wave number in Fourier space that we are going to care all the time for the perturbations goes as, well, actually to pi, but over lambda h, we basically can define the scale of the horizon in Fourier wave number as that one that kh times tau goes approximately of order unity. Now, outside of the horizon, particles don't know anything about each other, so if k times tau is much smaller than 1, those 2 points are completely not in causal connection. On the other hand, if k times tau is much larger than 1, we are going to be well within the horizon, and all the relativistic terms that depend on the expansion of the universe and the potential are going to basically be, sorry, and derivatives of the potential are going to be most of the times not contributing. And this is why, for example, in this case that we have here, we can go to the Poisson equation, because in this term, in this case, here we have factors of 1 over tau squared here. Here we have a k squared, so this factor with respect to this one goes as 1 over k squared times squared, tau squared, which for modes that are well within the horizon, that means that the denominator is much larger than 1, and therefore we can neglect this term here. And as I was saying, so the size of the horizon, for the Big Bang, this would be the end of inflation. We will have here that the horizon grows. With the kind of service that we have, we can probe this set of scales. And this is why I was saying before that in the CMB, we were probing the scales that are way outside of the horizon, like are much larger than the size of the horizon at the time of recombination, but they are still very homogeneous. And that's why inflation needs the exponential acceleration in order to have that the size of the horizon at early times in comoving units was much larger than it was today. Okay. So, as I was saying, this is the size of the curvature perturbations given by a curly R are related with the Hubble rate at the moment of horizon crossing. And at the end of the day, are frozen outside of the horizon. So it's only depending on this quantity. And from, like, since the field is going down the potential very slowly, even though the Hubble constant is almost constant, the Hubble parameter, sorry, the time derivative is smaller than 1. Sorry, than 0. So basically what this means is that at later times, scales that are going to leave the horizon, so larger scales, are going to be seeing a Hubble time, sorry, a Hubble expansion rate that is the one that determines the curvature perturbation that is slightly higher that is going to be in some time after. However, the whole thing with inflation is that these primordial perturbations are random. These depend on some fluctuating quantum fields. And at the end of the day, by definition, since R is a perturbation, the mean is 0, but we can't predict the actual value on a specific point for that perturbation because it's random. So, like, it depends on the specific realization of the universe that we have. And that's why what we care in the end about cosmology is about the covariance between these two for this field, because it's going to give us basically the distribution that we draw samples from in order to describe the field that we have. So for two modes, K and K prime, the covariance is given by 2 pi cube and the Dirac delta between the two fields times what we call the power spectrum. So at the end of the day, what we can predict from cosmology, assuming Gaussian perturbations, that is another of the predictions of single field slow roll inflation, we have that the underlying distribution that we draw samples from in order to populate the perturbations in our primordial universe has a variance given by the value of the power spectrum at that specific K. And the power spectrum of the primordial curvature, we can write it as, in some parametric form, as some amplitude, AS, K to the minus 3 of K over K pivot, NS minus 1. So for single field slow roll inflation and some other simple models of inflation, we can describe the power spectrum as a power law with a given amplitude and some pivot scale that is fixed. This is a convention for Planck. I think that is 0.05 inverse megaparsec, and some tilt, some spectral index for that power law. And this is one of the most important predictions of inflation, and is that since I was saying that the Hubble parameter decreases very, very slowly, this means that smaller scales that leave the horizon after what does the larger scales are going to have a smaller expansion rate. And if you remember what I said before, the curvature perturbations are related with h at the horizon crossing, and this means that NS has to be smaller than 1. And this has been actually corroborated by observations of the CMB. Right now, NS is of the order of 0.96, which is very consistent with H being almost constant, but not quite. Okay. And the good thing is that for that initial conditions in which we are completely outside of the horizon, such as R is constant, and we have the relationship between all our properties for each independent species, the assumption that those perturbations are adiabatic and that R is constant, we can relate the relationship between R and all our properties that we have. So for this case, we have that outside of the horizon, the initial conditions for all of these particles are like this. So the gravitational potential is minus 2/3 R, and since we are outside of the horizon, we don't know anything about shear because the particles don't see each other at these very large scales. We have that size minus 5. The monopole of relativistic species goes as 4/3 over R, and if you remember the relationship that I said before between matter and relativistic species for adiabatic components, for adiabatic perturbations, the perturbations in the matter goes as R. The dipole for the relativistic species goes as the divergence of phi, and finally, we can neglect any bulk velocity for the non-relativistic processes. Okay. Oops. So this was just a extremely quick and rushed primer for about cosmological perturbation theory. For those of you that are not that familiar with cosmology, that this may have been super chaotic. The problem is that for those of you that work in cosmology, this may be just a quick recap of things that you are familiar with. But with this, we can already discuss very briefly how matter perturbations and the gravitational potential evolve in the universe, which is going to be one of the main quantities that is going to be determining all of our discussions, because in the end, as we were seeing, the component, I erased it, the components and the evolution of photons and matter and so on is going to depend all the time in the gravitational potential. However, we can't go in full precision and being super robust in this derivation, because for that we need actually a solver of this big set of ordinary differential equations. So to do that, we are going to have and be making some approximations, and we are going to be solving analytically this evolution for the gravitational potential and the matter perturbations in specific regimes, where we will need, in order to match those regimes, the solutions from the numerical solver. So the main assumption that we are going to make is that since before recombination, photons and baryons are tightly coupled, we can consider them as a single fluid, as a single perfect fluid, and ignore any contribution from the quadruple or higher order moments. And that would not be the case for neutrinos, but since neutrinos contribute not that much to the energy of the universe, we are going to also keep them to the monopole and dipole, and consider a relativistic species altogether. And therefore, in that case, we have no shear, so we are going to assume that F for the relativistic species for L equal or larger to the quadruple is 0. This means that the shear is equal to 0, and basically we are going to have all the time the approximation that phi is equal to minus psi. And in this regime, the set of differential equations that we have, it's basically the solutions for the Boltzmann equation that I wrote before for each of the multiples. So we have that the time derivative of the monopole plus k times the dipole is minus 4 times the derivative of the gravitational potential. We have the equivalent equation for the dipole. Okay. And now we go to cold dark matter. And here, for example, you can see that the evolution for non-relativistic components and for relativistic components is very similar, but with a factor of 4/3 here. We have the similar for the time derivative, for the divergence of the velocity. And then we have a couple of sets that for the Einstein equations that are redundant, but sometimes we are going to be using one and sometimes we're going to be using the other. And this is basically, oh, I have them there. I don't need to copy them. Okay. As I said, we are going to consider very specific regimes, and we are going to be able to solve this, distinguishing very clearly between very large scales and very small scales. So on larger scales, the perturbations correspond to k very small. In this case, the transition between matter and radiation equality happens before horizon crossing. Transition through matter radiation equality outside of the horizon. And the transition, and then we are going to go through the horizon crossing. Already in matter domination. So at times that are after the moment of equality. And this is something that we are going to be seeing. We can use different variables for the evolution as an evolution variable. We can use the time. We can use the scale factor since it's monotonically growing. And also we can use the some other relationship between them that we are going to be using later. And then for the smaller scales, those are going to be the ones that k is much larger than 1, we have the horizon crossing before matter radiation equality, and the transition happens inside the horizon. Okay. And there's also something very important here, and is that we have some initial condition that was random, as I was saying before, but the set of evolution equation that we have is deterministic. So for any quantity that we care about, for example, the matter perturbations or the gravitational potential, we are going to be able to write it, for example, in terms of a transfer function times the primordial perturbations, which are the ones random. And this is random, but this one is deterministic. So as you can imagine, here we are going to have the same problem as before. We are not going to be able to predict the gravitational potential at a given specific point, but we are going to be able to predict its power spectrum by applying some deterministic evolution to the primordial power spectrum. Okay, so let's go at least qualitatively through the evolution of these properties given this simplifying equation in these specific regimes. So let's go first to larger scales and study the transition between matter radiation equality while we are outside of the horizon. So outside of the horizon, since k is much smaller than 1, and also remember that the condition for the horizon scale is basically the k times tau is approximately 1. Outside of the horizon, k times tau is much smaller than 1, so we can neglect this term, we can neglect this term, and we are not going to have contributions also from the velocities. So in this case, we have a set of, I'm not going to write it. So we basically have only the evolution of the monopole and the density in terms of the Einstein equations. And note that we start from a part in which phi is constant, and it goes as 2/3 of the curvature perturbations. What happens here, I don't have time to go through the math, but at the end of the day is that in this regime, if we basically play with equations and end up with a differential equation for phi, we find that at later times, after the transition, we have a drop of around 9/10 in our phi. So we have that phi is equal to 2/3 of R at radiation domination and 3/5 of the curvature perturbation in matter domination. Of course, this is not a step function. It's just like the transition is smooth, while you have contributions from the two components, from radiation and matter, for the evolution of the gravitational potential. And here is one of the first instances in which we have an actual discrepancy between this analytic approximated solution and the actual reality, and it's because since we have neutrinos that introduce some shear in the evolution of the universe, we are not quite in this situation, and in reality, instead of phi being 9/10 of 5/0, this is actually a bit smaller. This is like 0.86 or something like that, just as a curiosity. Okay. So for these scales, we have that outside of the horizon, and in matter domination, we have a constant potential with time. And actually, I need to rush through this, sorry. We can see that after going through through horizon crossing, and in that case, we basically can ignore these equations because in matter domination, we are not going to, like the contribution of the radiation to the potential is going to be minimal, so we can forget about that. But we can see that the gravitational potential is unaffected by when it crosses the horizon in matter domination, and phi is still constant. So here we have phi constant, but with a factor of 9/10 drop. And with the horizon crossing, phi is unaffected. So this means that for modes that enter the horizon during matter domination, the gravitational potential has always been constant. And that means once we are inside of the horizon and cross the horizon, go to very small scales, we can apply the Poisson equation, and actually the dark matter grows linearly with the scale factor. This is going to be true, and is going to be the case of the evolution of the perturbations at these scales until dark energy starts to contribute to the expansion of the universe, because basically what a constant gravitational potential means once we are within the horizon is that the contributions from being accreting matter and from the matter over densities to grow linearly with the scale factor due to the potential are exactly cancelled and counteracted by the fact that the universe keeps expanding. So you have two competing forces there for the evolution of the gravitational potential, and the two of them actually perfectly cancel. Now, once dark energy starts to contribute to the expansion of the universe, this is not the case because the expansion of the universe gets accelerated, and therefore the gravitational potential is going to start to dilute after. So in that case, since matter does not contribute at all to the evolution of the perturbations, because the total energy of the universe, these terms here, are only contributed by relativistic species, we can forget about these two equations, and we need to solve these two as function of also taking into account the Einstein equations, and then we will solve the matter growth in a second step. In this case, if we start connecting the evolution equations, we get to equation for the horizon, for the gravitational potential that goes as this. In this case, we can neglect, for example, this term because we are just going through the horizon crossing. And this is basically a damped harmonic oscillator. And this is because once we cross the horizon, photons and radiation, which is what dominates the evolution of the universe at that point, is in this tight coupling with baryons, and they oscillate. photons and baryons are going to be more dense in some regions, and in that regions, the radiation pressure makes them separate and overcomes the gravity and so on, and that's how you generate this acoustic wave. But that doesn't affect cold dark matter or anything, and what actually does is dilute the gravitational potential, and this is because while the radiation species oscillate with a constant amplitude, we have that the gravitational potential depends on the energy density of the universe with the factor of what is it? Here with a factor of h squared that goes as tau. So basically, psi here goes as the monopole over tau squared. In a very qualitative way. So basically what happens is that since photons don't cluster, but the universe keeps expanding, we don't have that contribution that cancels the expansion of the universe that we mentioned before, and the gravitational potential goes through these oscillations, but decreasing very fast. In such a way that we had something constant, and the moment we go through the horizon, for a given k, this goes down. This is as function of time, or a scale factor. For larger scales that enter the horizon a bit later, this is going to be constant and then drop. So this tells us that scales that are smaller, that have spent more time inside of the horizon, they have gone farther and a bigger suppression with respect to larger scales. The interesting part here is that even if the gravitational potential decays very quickly, since cold dark matter density doesn't know anything about baryons, doesn't know anything about photons, it just interacts gravitationally, very, very slowly, it keeps growing, it keeps clustering, and so on. So while we have this relation here, the matter density grows logarithmically with time. Yes. Okay, so in this case, we have that phi decays and oscillates, and delta C has a logarithmic growth. And we just have the final stage, in which for these modes that have entered the horizon after matter radiation equality, for these modes that are so small that have entered the horizon still during radiation equality, we have to see how the transition from radiation domination to matter domination affects to these modes for the growth of gravitational potential. And at the end of the day, we are going to be having the same equations that we had before for the larger scales, as we did the horizon crossing during matter domination, but with different initial conditions. So we need to match the oscillating and decaying mode here, or the logarithmic growth, with some solution and some other term that is going to be constant. But at the end of the day, since we are going to be in a situation that since since we are going to be in a situation in which is similar to this one, we are going to have that at the end of the day, phi is going to be constant, and delta cold dark matter is going to grow linearly with the scale factor. Therefore, from here, we can see already the general behavior that we can expect for the matter power spectrum. And that is basically that for very small values of k, very large scales, at the end of the day, except for this drop, the constant has been always, the gravitational potential has been always constant. So this transfer function is going to be practically unity. But for modes that crossed and entered the horizon before matter radiation equality, there has been a strong decay on the gravitational potential. So if we write here the matter power spectrum as function of k today, accounting for the fact that we have that PM is going to be proportional to T squared, which is the matter transfer function, and then the factor of KNS over KP NS minus 1. And this comes basically from applying the definition of the transfer function here and the Poisson equation to go from gravitational potential to matter density. Since this is very close to unity at large scales, we have almost a linear growth here. Then for scales that are the scale of the horizon at equality, we expect to have some turnover because we have some difference in the behavior, because for modes that entered the horizon at before matter radiation equality, we have the suppression, and the suppression is bigger the longer you have stayed inside of the horizon during radiation domination, and therefore here you have some suppression here that goes like this, and this is basically the connection between the two. So this gives us the relationship with matter radiation equality with this turnover. This goes as omega m h squared, if I remember correctly. Depends on the unit that you use for your power spectrum. So basically, from the position of this turnover, you can relate it with h squared and with omega matter. That's going to be important in the next days. And we have forgotten a couple of effects that I'm going to summarize now very, very quickly. We're going to go through some of them later, but basically, since we have ignored the effects of baryons, we need to take into account the fact that baryons also go through the oscillations because of the sound wave with the photons. We're going to go through that tomorrow, but they imprint some oscillations here, which is the baryon acoustic oscillations. Dark energy, as I mentioned before, suppresses the whole growth of perturbations at very low redshift because they grow slower than linearly because of the gravitational potential get washed. And finally, we have ignored the effect of massive neutrinos, but massive neutrinos free stream, and that means that they travel fast enough because they are very light, such as they are not going to be captured by gravitational potentials. And in that way, they basically wash these gravitational potentials down in scales that are smaller the free streaming scales. So in a phenomenological way, we can describe this free streaming scale for neutrinos as 0.06, the mass of the neutrino over 0.1 electron volts, and then this evolves with time in such a way that the free streaming scale for the neutrinos grows with time. This is because basically as the universe cools down, neutrinos are less and less relativistic. Actually, they go through the non-relativistic transition around redshift 100. And basically what this does is a suppression of the whole power spectrum as function of time and scale. So for a specific time, this would go something like this, where this would be KFS. But if we perform tomography, we can be very sensitive to this because since it depends on time and a scale with, like the scale depends on time, it's a very specific signature. So yeah, I think that we have to cut it for today. I apologize again for the extremely rushed class that we have today. This is going to be just the primer. The next days are going to be much more slower, just taking basically this behavior of the matter power spectrum and the things that we have learned in order to be building our knowledge about phenomenologically how the CMB works, how we can predict the power spectrum of the CMB anisotropies, and how that relates with the Hubble constant tension and the sigma tension. Okay, thank you very much.